Welcome to the second part of continuity and the intermediate value theorem. So now we're going to our last example of how to apply the limit. How to apply the definition of continuity into these functions. And here's our last example. So in the previous example, we had two parts. Now we have three parts, and now we need to find an a and a b that satisfies this piecewise function to be continuous everywhere. Okay? Well, I'm going to break it down, and this is not going to be correct, but it's going to be easy to understand what I'm doing here. So if I look at the first part of the function, it says here negative 17 when x is less than 3 and equal to. So it's going to be like this. That part for sure is correct. Okay? And then I'm going to go ahead and look at the third part. It's going to be a positive 3 when x is 1, but not including 1. So it's going to be an open dot and beyond. And then somewhere here in the middle, we have a linear function that's supposed to satisfy this continuous term here. So that means that the function has to do something like this. It could be like this. However, I don't know. Okay? And it has to close off right here too, okay, because of this part that says here equals to 1. Okay, so here's what we need to do. We need to look at the left and right hand limits of these two values right here. There's one there and one there, one there and one there. So we're gonna go ahead and split this off. So we need to analyze the limits around x equals negative 3 and x equals positive 1. So if you look at this, this is the left side of negative 3, and this is the right side of negative 3. So we're going to go ahead and look at x equals negative 3. And if you remember from the last example that if we can find the left hand limit and the right hand limit, we equalize them and we solve for the variables. So here is the left-hand limit. The left-hand limit is simply just 17. Negative 17. Okay? There is no x to plug in. So we just say the limit of a constant is the negative 17. The right-hand limit. Well, if we plug in negative 3 into the ax plus b, we see that we get a times negative 3. Oops, let me clean that up. A times negative 3 plus b. By definition of a limit to be existing, these two limits must equal to each other. So I'm going to go ahead and write negative 3a plus b is equal to a negative 17. Now let's go ahead and analyze at x equals positive 1. So the left hand limit at x equals 1 is this function, because here is the left part. Here is the left part at x equals 1. So we're going to simply plug in the limit into the ax plus b. So it's going to be a1 plus b. The right hand limit, so beyond 1, is actually just only 3. Since the limits have to equal to each other, we're going to equalize the limits. So a times 1 is just a plus b equals 3. Now what I have to do, now I have two equations with two unknowns, and if you remember your algebra 2, we can solve these by using a system of linear equations. So negative 3a plus b is equal to negative 17. A plus b is equal to 3. Now, I can add up and down, but I'm still stuck with two unknowns. So I have to eliminate a variable. I have to eliminate. And the easiest one to eliminate, okay? The easiest one to eliminate is the b part, okay? So I notice I have a positive b, another positive b, so I'm going to go ahead and make one of them into a negative, and by doing that I have to change every single sign of each term so that I have a negative 3a plus b is equal to negative 17. Okay, now the top didn't change because I didn't do anything. The bottom changes. Now I have a negative a minus b is equal to negative 3. Now we can go ahead and add up and down. We have negative 4a and we have plus 0b is equal to a negative 20. Dividing 4 to both sides, negative 4, we get a is equal to 5. Box that answer. Now you can choose. Which one do you want to plug it into? You could plug it into this guy or this guy. I always choose to plug it into the easiest one. So let's go ahead and plug in A and solve for B. B is negative 2. And you could do the same thing for this side. If I do it over here, if you're the type that wants to verify themselves and prove themselves that it still works, well, it still does work. Now I have a negative 15 plus b is equal to negative 17. If I add 15, I still get b is equal to negative 2. So it doesn't matter which one you choose. Those are my two answers. In other words, if a is equal to 5 and b is equal to a negative 2, so a negative 5x plus 2 would be this black line right here. Okay, now moving on to the intermediate value theorem. Now, just by like a definition of the intermediate value theorem, it seems very overwhelming. Okay, so as I state the intermediate value theorem, I am gonna draw a picture. Okay, it says here, if f of x is continuous on the closed interval to a and b. Okay, so we have a closed interval a, b. If f is continuous on a to b, closed, and if f of a does not equal f of b, so this means y. This means y values. This is the y at x equals a. This is my f of a, or rather, I should do it like this. So I should make it a little more higher. I'm gonna call this f of a, and I'm gonna call this. I'm gonna make it easier for you guys. I'm gonna call this f of b. So I'm gonna do. I'm gonna call this f of b right here. F of b. It says here, if f of b and f of a do not equal. Obviously they don't equal, because look, f of a is on the top, f of b is on the bottom, and k is in between f of a and f of b. K is another y value. Then, okay, so let's stop. This function is continuous, so I'm gonna draw it however I want to draw. I'm gonna draw like this. Okay, there is my f of x. It's continuous, obviously, right? There's no holes or gaps. Okay, so far I talked about condition 1, condition 2, and let's talk about condition 3. Condition 3 says if k is in between f of a and f of b. So in red, I'm going to say that this is my k. If k is in between f of a and f of b, notice that it is in between f of a and f of b, then there exists a c. Now they're talking about an x value between a to b, such that f of c, notice this is my x, is equal to a k, and that is my y. So what this means is that there exists a c value in between a to b that gives me a k that's in between f of a to f of b. In other words, to put this in its most simplest terms, the intermediate value theorem is known as the existence theorem. In other words, there exist points in between a to b if the function is continuous. That is why it's called the intermediate value theorem. We're talking about the interior points. Okay, so one way that I taught this last year is I drew a plane. Okay, so I'm gonna go ahead and delete all this. So if you don't have this, just pause it and take down the notes. I taught it like this last year. I taught it, let's say you have a plane. So you got a plane, and this plane is at a 20,000 foot altitude. Something happens to the plane, pilot loses control, I don't know, boom. Everyone dies, okay? So that would be the altitude of 0 feet, okay? Here's my question. does the plane's trajectory, look at this trajectory right here, does this plane ever cross the altitude of, I don't know, 7,000 and no, 701 feet? Does it ever cross that altitude as it's going down, plummeting into